If you throw a stone, it follows a path. If you roll a ball, it slows down and stops. If you drop something, it falls to the ground. These patterns repeat every day of our lives, so our brains quietly assume the universe behaves in a predictable, orderly way. This expectation is not unreasonable. In fact, it worked extremely well for centuries. The rules behind these everyday motions were famously described by Isaac Newton in the 1600s. Newton showed that the motion of objects follows precise mathematical laws. If you know the position of an object, how fast it is moving, and what forces are acting on it, you can calculate exactly what will happen next. Throw a baseball, and physics can tell you where it will land. Fire a cannon, and you can predict the arc of the cannonball. Send a spacecraft into orbit, and the same laws explain how it circles the Earth. This view of the universe feels very natural. The world behaves like a gigantic machine with gears that follow clear rules. If you know the starting conditions, the future is determined. In this picture of reality, objects have definite properties at all times. A ball is always in one place. It moves along one path. It cannot be in two places at once, and it certainly cannot explore every possible path through space. These ideas form the foundation of what physicists call classical physics. For objects the size of apples, cars, planets, and stars, classical physics works incredibly well. It allowed humanity to build bridges, predict eclipses, and eventually land astronauts on the moon. So for a long time, scientists believed that the basic structure of reality had been figured out. But near the end of the 19th century, something strange began to happen. Physicists started studying phenomena that occur at extremely small scales, the scale of atoms and light. At first, they assumed the same classical rules would apply there as well. After all, why would the universe behave one way for large objects and a completely different way for small ones? Yet experiment after experiment started producing results that simply didn't make sense under classical physics. Light sometimes behaved like a wave, spreading out and interfering with itself. But in other experiments, it behaved like tiny packets of energy called photons. Electrons, which were thought of as small particles, sometimes spread out like waves across space. And the deeper scientists looked, the more confusing the behavior became. The strange rules governing this microscopic world eventually formed a new branch of physics known as quantum mechanics. Quantum mechanics did something extraordinary. It explained experiments with astonishing accuracy. Its predictions worked perfectly in laboratories. But there was a problem. The theory described a universe that behaves nothing like the one our intuition expects. Instead of certainty, there was probability. Instead of clear paths, there were waves of possibility. Instead of objects having definite properties, reality seemed to exist in multiple potential states at once. At the atomic scale, the universe was not behaving like a neat mechanical clock. It was behaving like something far stranger. And that discovery forced physicists to confront an unsettling idea. The everyday world we experience might only be a simplified surface of a much deeper, much weirder layer of reality. When physicists first began exploring the microscopic world, they expected the same rules that govern falling apples and moving planets to apply. The assumption seemed obvious. The universe should follow one consistent set of laws at every scale. If classical physics works for large objects, it should also work for tiny ones. But early experiments with light began to reveal something deeply puzzling. For a long time, light was understood as a wave. This idea had strong experimental support. Waves can spread out, overlap, and interfere with each other. Ocean waves do this, sound waves do this, and experiments showed that light behaves in the same way. If two light waves overlap, they can strengthen each other or cancel each other out. This phenomenon, called interference, creates patterns of bright and dark regions. Such patterns appear in carefully designed optical experiments and confirm that light behaves like a wave moving through space. So physicists were confident about one thing: light is a wave. Then something unexpected happened. Experiments studying how light interacts with metal surfaces produced results that made no sense if light were purely a wave. When light shines on certain metals, it can knock electrons out of the surface. This process is known as the photoelectric effect. According to classical wave theory, increasing the brightness of light should gradually give electrons more energy. A brighter wave should push harder on the electrons. But the experiments showed something very different. Below a certain frequency of light, no electrons were released at all, no matter how intense the light became. But once the frequency crossed a specific threshold, electrons suddenly started flying out of the metal, even if the light was very dim. This behavior was extremely strange. It suggested that light does not deliver energy in a smooth, continuous flow the way waves normally would. Instead, energy seemed to arrive in tiny, discrete packets. In 1905, Albert Einstein proposed a bold explanation. He suggested that light behaves as if it is made of individual particles of energy. These particles are now called photons. Each photon carries a specific amount of energy determined by the light's frequency. If the photon has enough energy, it can knock an electron free from the metal. If it doesn't, no amount of additional photons will help. This idea solved the puzzle perfectly, but it created a new one. If light is made of particles, how does it still produce wave interference patterns? Waves interfere, particles normally do not. Yet experiments showed both behaviors clearly. Light was acting like a wave in some situations and like a particle in others. Physicists tried to understand which description was correct. Was light really a wave, or was it actually a stream of particles? The answer turned out to be deeply unsettling. Light was somehow both. This strange dual nature became known as wave-particle duality. It means that certain things in nature cannot be described purely as waves or purely as particles. Instead, they possess characteristics of both depending on how we observe them. At first, scientists hoped this bizarre behavior might apply only to light, but further experiments quickly destroyed that hope. Electrons, objects that were clearly believed to be particles, also produced wave-like interference patterns under the right conditions. Matter itself seemed capable of behaving like a wave. The deeper physicists investigated, the more they realized that classical intuition was failing. The microscopic world was not following the comfortable rules that worked so well for everyday objects. Instead, the behavior of nature at small scales appeared to obey a completely different framework, one that required a radically new way of thinking about what reality actually is. To really see how strange the microscopic world is, physicists often turn to one deceptively simple experiment. It is known as the Double-Slit Experiment, and despite its simplicity, it has become one of the most important demonstrations in modern physics. The setup is straightforward. Imagine a wall with two narrow openings cut into it. Behind that wall is a screen that records where incoming particles land. In front of the wall, a device fires particles toward the slits. Before performing the experiment with anything exotic, it helps to imagine what would happen with ordinary objects. Suppose you throw tiny balls toward the wall. Some balls pass through the left slit, and others pass through the right slit. When they hit the screen behind the wall, they form two clusters. One cluster lines up with the left slit, and the other cluster lines up with the right slit. Nothing surprising there. Each ball travels along a clear path and lands in a predictable region. Now imagine repeating the same experiment with waves instead of particles. Think about water waves moving toward a barrier with two openings. When waves pass through those openings, they spread out and overlap with each other. Where the peaks of the waves meet, they strengthen each other. Where a peak meets a trough, they cancel out. This creates a repeating pattern of stronger and weaker wave activity. If you measured the wave intensity on a screen, you would see a series of bright and dark stripes. This pattern is known as an interference pattern, and it is a clear signature of wave behavior. So if particles behave like particles, you should see two clusters. If waves pass through the slits, you should see an interference pattern of stripes. Physicists then performed the experiment using electrons. Electrons were known to be particles. They have mass charge and can be detected as individual impacts on a screen. So the expectation seemed obvious. Electrons should behave like tiny balls and produce two clusters. But the screen revealed something completely unexpected. Instead of two clusters, a pattern of multiple stripes slowly appeared. The electrons were forming an interference pattern exactly like waves do. This result was shocking. Somehow electrons were behaving as waves when passing through the slits. At first, some scientists suspected that the electrons might be interacting with each other as they traveled. Perhaps they were bouncing off one another in complicated ways that created the pattern. So researchers tried an even more careful version of the experiment. They fired electrons one at a time. One electron leaves the source. It travels toward the barrier. It passes through the slits. Then it hits the screen as a single dot. Then another electron is fired. Then another. Each electron arrives individually, producing one tiny dot on the screen. But as thousands of electrons accumulate over time, something remarkable appears. The collection of individual dots slowly builds the same interference pattern. The only way to explain this pattern is to imagine that each electron behaves like a wave passing through both slits at once and interfering with itself. Yet when it strikes the screen, it always appears as a single localized particle. It is as if the electron spreads out across space like a wave while traveling, explores multiple possibilities at once, and only becomes a definite particle when it is detected. This behavior is deeply strange because it contradicts the way we normally think about objects moving through space. In everyday life, objects follow specific paths. A baseball cannot pass through two doors simultaneously. A car cannot drive down every road at once and then later decide where it actually went. But in the microscopic world, particles seem to behave exactly this way. And the more carefully physicists studied the experiment, the more mysterious it became. Because when scientists tried to observe which slit the electron actually passed through, the entire interference pattern suddenly vanished. When physicists realized that particles could produce interference patterns, they faced a difficult question. If an electron behaves like a wave passing through both slits, what exactly is that wave doing? How does a single particle explore multiple possibilities before finally appearing at one point on a screen? One of the most insightful ways to think about this came from the physicist Richard Feynman. Instead of imagining a particle traveling along one definite path, Feynman proposed something much stranger. According to his idea, when a particle moves from one place to another, it does not simply choose a single route. Instead, it explores every possible path that could connect those 2 points. This sounds impossible at first, but it becomes easier to grasp with a thought experiment. Imagine you want to walk from your house to a nearby store. In ordinary life, you would pick a sensible route. Maybe you follow the sidewalk, cross the street at a corner, and arrive at the door. Your path is clear and continuous. But now imagine a universe where you do not choose just one path. Instead, you simultaneously take every possible route. You walk along the sidewalk. You cut across the grass. You wander through alleys. You circle the block several times before arriving. You even take absurd routes, climbing fences, looping around buildings, or zigzagging back and forth. In everyday life, these strange paths never happen. But in the microscopic world, quantum theory suggests that particles consider all of them. Each possible path contributes a small influence to the final outcome. Some paths reinforce each other, while others cancel out. When physicists add up all these contributions mathematically, they obtain a prediction of where the particle is most likely to appear. This idea became known as the path integral formulation of quantum mechanics. What makes this approach remarkable is that it does not assume a particle follows one trajectory. Instead, reality is described as a combination of all possible histories. At first, this seems wildly impractical, even absurd. But the mathematics works beautifully, and it produces exactly the interference patterns observed in experiments like the Double-Slit Experiment. Interestingly, this strange rule also explains why large objects behave normally. Consider a baseball traveling through the air. In principle, the baseball could also explore countless paths. It could arc smoothly toward the catcher, but it could also take wildly improbable routes, twisting and looping through space. However, for large objects, those bizarre paths cancel out almost perfectly when their contributions are added together. Only the sensible path survives in the final calculation. As a result, the baseball appears to follow the familiar trajectory predicted by classical physics. At very small scales, however, the situation changes. For electrons, photons, and other microscopic particles, those unusual paths do not cancel out completely. Their contributions remain significant, allowing interference effects to emerge. This means the strange behavior seen in quantum experiments is not caused by experimental error or hidden disturbances. It appears to be a genuine feature of nature itself. A particle moving through space is not simply traveling from point A to point B. Instead, it behaves as if it is sampling a vast landscape of possibilities. The path we eventually observe is the result of countless invisible alternatives interacting with one another. From this perspective, reality at the smallest scales is not built from rigid trajectories, but from a subtle interplay of probabilities and possibilities. The strange behavior of particles becomes even more puzzling when physicists try to observe what is actually happening during an experiment. At first glance, it seems reasonable to assume that the problem with the double-slit experiment is simply that we do not know which slit the electron travels through. If we could place a detector at each slit and watch carefully, we should be able to determine the particle's path. So scientists tried exactly that. They installed extremely sensitive detectors near the slits in order to observe which opening the electron passed through. The idea was simple. If an electron behaves like a wave passing through both slits, the detector should reveal that. If it behaves like a particle choosing one slit, the detector should reveal that too. But when the experiment was performed, something unexpected happened. The interference pattern disappeared. Instead of the familiar pattern of many stripes, the screen showed only two clusters, exactly what you would expect from ordinary particles passing through two openings. The electrons now behaved like tiny objects traveling along definite paths. The only difference between this experiment and the earlier one was the presence of measurement. The act of observing the electron's path changed the outcome of the experiment. This result is deeply unsettling because it seems to suggest that observation itself influences the behavior of physical systems. It gives the impression that reality behaves differently depending on whether it is being watched. However, the situation is subtler than it first appears. In quantum physics, observation does not necessarily mean a conscious observer looking at the system. Instead, it refers to any interaction that extracts information about the system's state. A detector, a measuring device, or even certain interactions with the environment can count as a measurement. To understand why measurement matters, physicists describe particles using a mathematical object known as the wave function. The wave function does not describe a particle as a tiny object with a fixed position. Instead, it represents a spread of possible outcomes. It tells us the probability of finding the particle at different locations or with different properties. Before measurement, the particle exists in what is called a superposition of possibilities. It is not located at one specific point. Instead, its potential locations are spread out across space according to the wave function. When a measurement occurs, the situation changes abruptly. The spread of possibilities suddenly reduces to a single result. The particle appears at one specific location, and the other possibilities disappear. This transition is known as wave function collapse. The mathematics of quantum mechanics predicts the probabilities of different outcomes with extraordinary precision, but the theory itself does not fully explain why this collapse happens. It simply states that when a measurement is made, the wave function changes. This raises difficult philosophical questions. Before measurement, does the particle truly exist in multiple states at once? Or is the wave function merely a tool that describes our lack of knowledge? Different interpretations of quantum theory answer these questions in different ways, and physicists continue to debate the issue. What experiments clearly show, however, is that measuring certain properties of a system changes how that system behaves. The microscopic world does not reveal all of its properties simultaneously. Instead, the act of extracting information appears to play a direct role in shaping the outcomes we observe. This is one of the reasons the quantum world feels so unfamiliar. In everyday life, objects possess definite properties, whether we look at them or not. A chair has a position even when nobody is observing it. But in the microscopic world, reality seems to be structured around possibilities that only become definite when a measurement forces them to do so. And despite decades of study, the deeper reason behind this behavior remains one of the central mysteries of modern physics. One reason quantum physics feels so difficult to accept is that our intuition was never built to understand it. Human brains evolved to survive in a world filled with objects that are large, slow, and predictable. We learned to judge distances, track moving animals, throw tools, and navigate terrain. All of these tasks involve objects that follow the rules of classical physics. In that familiar world, objects have definite locations. A stone is either on the ground or in your hand. A bird is either in the sky or on a branch. When something moves, it follows a continuous path through space. Because these patterns repeat throughout our lives, our minds quietly assume they represent the basic structure of reality. But the microscopic world does not share those patterns. When scientists began developing the mathematical framework of quantum mechanics in the early 20th century, they quickly discovered that the equations worked extremely well. They accurately predicted the behavior of atoms, molecules, and subatomic particles. The theory explained why atoms form stable structures, how light interacts with matter, and why certain materials conduct electricity while others do not. Despite this success, many of the scientists who helped create the theory felt uneasy about its implications. One of them was Albert Einstein. Einstein contributed important ideas to quantum theory, including the explanation of the photoelectric effect. Yet he was deeply troubled by the idea that fundamental events in nature might be governed by probability rather than certainty. In classical physics, uncertainty arises because we lack complete information. If we cannot predict the exact landing point of a thrown ball, it is usually because we do not know all the details of the forces involved. With better measurements, we could in principle calculate the exact outcome. Quantum theory suggests something much more radical. According to the mathematics, some aspects of nature are genuinely uncertain. Even with perfect knowledge of the system, certain pairs of properties cannot be known simultaneously with unlimited precision. This limitation is described by the Heisenberg uncertainty principle. The principle states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not simply a technical limitation of our measuring devices. It appears to be a fundamental feature of reality. Einstein struggled with this idea. He believed that nature should ultimately follow deterministic laws. In a famous remark, he expressed his discomfort by saying that he could not believe the universe operates through pure chance. Yet experiment after experiment confirmed the predictions of quantum theory. Particles sometimes behave in ways that can only be described in terms of probabilities. When a radioactive atom decays, the exact moment of decay cannot be predicted, even in principle. Quantum mechanics can only tell us the probability that decay will occur within a certain time interval. This is profoundly different from the deterministic picture that guided physics for centuries. Part of the difficulty lies in the fact that quantum objects do not resemble anything in our everyday experience. They are not simply tiny versions of familiar objects like grains of sand or miniature planets. Instead, they behave like entities that blur the boundary between particles and waves. Their properties can remain undefined until interactions occur. Their behavior can only be described statistically. Our minds try to visualize these processes using ordinary images, but those images inevitably fail. The true structure of the quantum world seems to resist the kinds of pictures that our brains evolved to understand. As a result, Quantum physics often feels less like discovering a new machine inside nature and more like uncovering a deeper layer of reality that operates according to rules very different from those we encounter in daily life. Despite how strange the quantum world appears, there are several things physicists understand with remarkable confidence. Over the past century, thousands of experiments have tested the predictions of quantum mechanics. Again and again, the results have matched the theory with extraordinary precision. In fact, quantum mechanics is widely considered the most accurate scientific theory ever developed. Some of its predictions have been verified to more than 10 decimal places. Technologies such as lasers, semiconductors, and magnetic resonance imaging all rely on principles derived directly from quantum theory. So although the ideas may feel counterintuitive, the evidence supporting them is extremely strong. One of the most important lessons of quantum mechanics is that particles are not best described as tiny solid objects moving through space. Instead, they behave more like patterns of probability. The mathematical tool used to describe these probabilities is called the wave function. The wave function contains information about all the possible outcomes that could occur when a measurement is made. It tells us where a particle might be found and how likely each possibility is. Before a measurement takes place, the particle does not appear to have a single definite location. Instead, its potential positions are distributed across space according to the wave function. This situation is often described as a superposition of states. In simple terms, the particle exists in multiple possible configurations at the same time until an interaction forces one outcome to become definite. Although this idea can sound mysterious, it is supported by many experiments. Interference patterns such as those seen in the Double-Slit Experiment are clear evidence that quantum systems behave as if multiple possibilities are present simultaneously. Another central feature of quantum mechanics is the role of probability. When physicists calculate the behavior of a quantum system, the result is not a single predicted outcome, but a set of probabilities. The theory tells us the likelihood of different results, but does not determine which specific result will occur in an individual experiment. This probabilistic nature of reality is closely related to the Heisenberg uncertainty principle. The uncertainty principle reveals that certain pairs of physical properties cannot both be precisely defined at the same time. Position and momentum are the most famous example. The more precisely one property is known, the more uncertain the other becomes. This limitation does not arise from experimental imperfections. Instead, it reflects a fundamental structure built into the laws of quantum physics. Another well-established aspect of quantum theory is that interactions between systems play a crucial role in determining outcomes. When a quantum system interacts with a measuring device or its surrounding environment, the range of possibilities described by the wave function can change dramatically. In practice, these interactions often cause quantum systems to behave more like classical objects. The delicate interference effects that exist at microscopic scales tend to disappear when many particles interact with one another. This is one reason why everyday objects do not display obvious quantum behavior. A baseball, for example, contains an enormous number of atoms constantly interacting with their surroundings. These interactions effectively suppress the fragile quantum patterns that would otherwise appear. As a result, the baseball follows the familiar trajectory predicted by classical physics. What emerges from all of this is a picture of reality that is both precise and subtle. Quantum mechanics does not describe a world of rigid certainty. Instead, it reveals a universe where possibilities evolve according to strict mathematical rules, and where definite outcomes emerge only through interactions that select one result from many potential alternatives. Even though quantum theory predicts experiments with astonishing accuracy, it leaves physicists with deep unanswered questions about the nature of reality. The equations work beautifully, but interpreting what those equations mean is far more difficult. One of the central puzzles involves the wave function. In the mathematical framework of quantum mechanics, the wave function contains all the information that can be known about a system. It evolves smoothly over time according to precise equations. Yet when a measurement occurs, the wave function appears to suddenly reduce to a single outcome through what is often called wave function collapse. The strange part is that the theory itself does not clearly explain what causes this collapse. In the mathematical description, the wave function spreads out across many possibilities, representing multiple potential outcomes at once. But when a measurement is made, only one of those possibilities becomes real in the experiment. The others vanish from observation. Physicists can calculate the probability of each outcome with great precision, but the theory does not tell us why a particular result appears in a specific event. This situation has led to a wide range of interpretations of quantum theory. Each interpretation attempts to explain what the mathematics is really describing. One of the earliest and most widely taught interpretations is the Copenhagen interpretation. According to this view, the wave function does not represent a physical object in space. Instead, it represents our knowledge or information about the system. When a measurement occurs, that knowledge is updated, and the wave function changes accordingly. In this interpretation, quantum mechanics does not describe an underlying reality directly. It provides a set of rules for predicting the results of experiments. Some physicists are satisfied with this perspective, while others find it unsatisfying, because it avoids answering deeper questions about what actually exists before measurement. Another interpretation proposes a far more radical possibility known as the many worlds interpretation. In this view, the wave function never collapses at all. Instead, every possible outcome described by the wave function actually occurs. When a measurement is made, the universe splits into multiple branches, each containing a different result. In one branch, a particle appears in one position. In another branch, it appears somewhere else. Each branch continues evolving independently. This interpretation preserves the smooth mathematical evolution of the wave function, but introduces the idea that reality may consist of an enormous number of parallel worlds. Other physicists have explored the possibility that hidden variables might exist beneath quantum theory. These hypothetical variables would determine the outcomes of quantum events in a deterministic way, even though they remain inaccessible to current experiments. However, many tests inspired by the work of John Stuart Bell suggest that any hidden variable theory must involve non-local connections between distant particles. These results place strong constraints on how such theories could work. The situation leaves physicists in a curious position. On one hand, quantum mechanics provides incredibly accurate predictions and forms the foundation of modern technology. On the other hand, its deeper meaning remains uncertain. Different interpretations offer different pictures of what reality might be like, but none has been universally accepted. This means that one of the most successful scientific theories ever created is also one of the most philosophically mysterious. The equations describe how the quantum world behaves, yet the underlying nature of that world remains an open question. And that uncertainty continues to drive both theoretical research and philosophical debate about what the universe is truly made of. As strange as the quantum world appears, one of the most important lessons it offers is that the reality we experience every day is not the deepest layer of the universe. The familiar world of solid objects, clear trajectories, and definite positions emerges from something far more subtle happening underneath. In everyday life, matter appears stable and predictable. A table feels solid. A ball follows a clear path when thrown. The moon moves along a precise orbit around Earth. All of these behaviors are accurately described by the laws of classical physics, developed by scientists such as Isaac Newton. But when scientists examine matter at extremely small scales, those simple pictures begin to dissolve. Atoms themselves are mostly empty space. Inside them are electrons moving in ways that cannot be described as tiny planets orbiting a nucleus. Instead, their behavior is governed by the rules of quantum mechanics. An electron in an atom does not travel along a fixed circular path. Rather, it exists in a distributed pattern described by the wave function. This pattern represents the probability of finding the electron in different regions around the nucleus. What we perceive as a stable atom is actually the result of quantum probabilities forming stable structures. The shapes of atomic orbitals, the chemical bonds between atoms, and the structure of molecules all arise from the underlying mathematics of quantum mechanics. Even the solidity of everyday objects comes from quantum effects. When you press your hand against a table, the atoms in your hand do not physically collide with the atoms in the table the way two billiard balls would. Instead, electromagnetic forces and the quantum behavior of electrons prevent the atoms from passing through one another. The stability of matter depends on principles such as the Pauli exclusion principle, which prevents certain particles from occupying the same quantum state. Without this rule, atoms would collapse and the familiar structure of matter would not exist. In other words, the ordinary world we experience is built entirely on top of quantum laws that operate invisibly at microscopic scales. What appears to be a simple object is actually an intricate arrangement of quantum systems interacting with one another. Each atom contains particles whose behavior is described not by precise positions, but by evolving probabilities. When enormous numbers of these particles interact, the delicate quantum patterns that govern them tend to average out. The strange interference effects seen in experiments like the Double-Slit Experiment become extremely difficult to observe in large systems. This process, often related to interactions with the environment, helps explain why classical behavior emerges in everyday situations. As a result, the world we perceive feels stable and deterministic, even though it is built upon probabilistic foundations. This realization subtly changes the way we think about reality. What we experience directly with our senses is not the fundamental layer of nature. It is a large-scale pattern that emerges from countless microscopic processes. At the deepest level currently known to physics, matter is not made of tiny solid pieces arranged like grains of sand. Instead, it appears to consist of dynamic systems described by mathematical waves of possibility. Particles, fields, and interactions combine to produce the stable structures we call atoms, molecules, and objects. From this perspective, the ordinary world is not separate from the quantum world. It is the visible surface of a much deeper structure, where probabilities evolve and interact continuously to shape the reality we observe.